Okay, so I only had one quick question. It just had to do with number 1 on the take home.
Oh yeah.
It was just the plus, is like the little plus next to the Z. Is that just saying it needs to be positive?
Yeah, so it only has to work on positive integers.
Okay, that was like my only question with the whole thing.
Oh, okay. All right.
But yeah, okay, just wanted to make sure that was the right way. Okay, thank you.
All right, thank you.
I need help with anything else. But
that's easy.
Yeah, thank you.
Thank you, Zach. How are you? Do you have questions?
I do. So mine is simple as well. On number 7, I'm just sort of stuck on basically the first part. I'm having difficulty getting 1 in that spot where 13 is.
Oh, so we're working mod 29, right?
Yes.
So you have this. Now, normally, if these were taken over the real numbers, we would just say multiplied by 1/13, right? Because the reciprocals exist. But since we're working mod 29, all inverses exist. So what you want to do here is multiply row 1 by the inverse of 13. And in Canvas, I uploaded, like if you go to, hold on, let me get to the right course. If you go to the page that has like the notes and videos, like the content, there should be a PDF. Oh yeah, the last row that has the inverses, mod 29.
Okay. We just multiply row 1 by the inverse of 13 to get that to be 1.
Yeah, because by definition, so 13 has an inverse because it's relatively prime to 29. And once you find that inverse, multiplying any number by its own inverse will give you 1. So that's how you get a 1 where you need it in any location. And then the rest of it works the way it normally would, where you add like a multiple of one row to another row. You're just going to reduce everything mod 29 each step of the way.
Okay. All right. Then I could probably start attempting that program or that problem now. So that's all I had.
Oh, all right. Well then, great. If you get stuck, I'll be sitting in here in these office hours probably until, if people show up, I'll be here for the whole time. If I don't get anybody, I'll probably be here at least until 3. But if you get stuck, I just want to send you to the right example. So it was in the last section. Here it is. In example 545, we found the inverse of a matrix mod 29.
Yeah, my notes on that were a little bit scribbly, so I was having difficulty.
Your notes were scribbly? Are you really?
They were
for real?
They're unlegible to me, so I was like, yeah. But thanks. If I have another question, I'll hop back in.
Okay. All right. Thanks.
Yep.
Hey, how you doing?
I'm all right. How are you?
Doing all right.
How can I help?
So, actually making pretty good progress.
Oh, good.
1, 2, 5, 6, 7, and I think 8 are mostly in the bag. So for 8, because of the conversation we had last time, I pretty much understand why 32 doesn't work, because it's not prime, so there's no guarantee that you'll be able to decrypt the message. But, I looked at a list of primes, and it looks like the next one would be 37. You just have to fill up the extra characters with gibberish or whatnot to make the message work.
Yeah, like just some other characters.
Okay. So I just got to write that down.
Yeah.
So looks like I was just in the process of neatening everything up. Number 4, and What was the last part of number 3 I did? It was reflexive and transitive.
Right.
Which
Did we
means
talk about?
symmetric.
I think we talked about reflexive and symmetric.
Symmetric.
Right. Like, I mean,
I still got the thing pulled up here.
because this is the one where we say that x is
You
related
gotta
to
prove an
y if x
equivalent,
minus y is an integer. So when we talked about reflexive, you pretty much had it, right? I mean, you look at
Yeah, because 0.
yeah, and then symmetric. I think you kind of were all set on that one, if I remember correctly. Oh yeah, I guess I didn't make many notes about it because I think we just talked briefly. But like symmetric means if x is related to y, then y is related to x, right?
Right.
So let's say, suppose x is related to y. What does that mean?
If x is related to y, then x minus y is an integer.
Mm-hmm.
And then we got into the number 3.14.
Right, well, yeah, I was saying, like, let's just get, that was before, that was, like, kind of near the beginning. I said, let's just get a feel for this.
Yeah.
For this relation, and I said, tell me what's related to 3.14, and then that's when you kind of started to see, oh yeah, I just need, like, I think you said like 0.14 or like 2.14, right? If they have like the same decimal part, they end up being related. But
Right.
if so we said, suppose x is related to y, and you said, well, then x minus y is an integer. If I want to answer the question, is y related to x, what is it that we look at?
I mean, so yes, because it doesn't define related as y minus x. It defines it as x minus y.
Well,
so if x minus y is related, then
well,
they're
it defines, so x related to y, right? If and only if x minus y is an integer. But it's not that it doesn't define y related to x. It just says whatever's on the left side is related to whatever's on the right side.
Okay.
If when I do the subtraction, I get an integer. So when I think about reversing the order, and I want to say, what does it mean to say y related to x? What is it that we look at? What's the expression we're going to look at?
I got lost again.
So
Okay,
the way it's defined,
x minus y is an integer.
so right, so and that's because x is related to y. And when we say x is related to y, that order matters. We're saying take whatever's on the left side of the delta and subtract whatever's on the right side, so you get x minus y is an integer. So if we want to know if y is related to x, what is it that we have to look at? What's the difference that we have to look at?
The difference would be to see if it's still an integer after
To see
it's
if what's still an integer.
y minus x.
Yeah, right? Left side minus right side. Perfect. Okay.
Yeah.
What happens when we reverse the order of subtraction? Like, think.
When you reverse the order of
Like,
subtraction.
let's think. In example first. Like, if I compare 5 minus 3 versus 3 minus 5.
Mm-hmm.
So 5 minus 3 gives us 2. 3 minus 5.
Negative 2.
Right. So what changes when we reverse the order of subtraction?
The sign.
Yep. So if I'm looking at y minus x, that's going to be the negative of x
Whatever
minus
x minus y is.
Yeah. That's all you got to... And in fact, you could even see this algebraically, right? If you distribute that negative, right, you'll recover y minus x. So, and what do we know about x minus y?
That they are related.
So, well, we know that x is related
There's
to
an
y,
integer.
so x minus y is an integer, so what about negative x minus y?
It also has to be an integer.
There you go.
Okay.
You'll make similar arguments with transitive, right? Because with transitive, you're going to suppose x is related to y and y is related to z, right? And then so that means we know something about x minus y, and we know something about y minus z. Now I'm going to bring you back to something we did before the break. One of the last things we did when we were still in class together, and we looked at this relation. It's example 434, and we said that, and this was a relation on the integers. Like, it's a different relation, but we look at a similar expression. We said A is related to B if and only if A minus B is even, right? So finding out, learning about this relation was still all about looking at the difference A minus B, right? When we went down to show that it was transitive, we said, let's suppose, right, that A is related to B and B is related to C. That got us some stuff. We knew that A minus B had to be even and B minus C had to be even. And then, here's sort of our technique. We had to look at A minus C, right? If we wanted to show that A was related to C, we had to look at that difference. And we used a little algebra here, and we said, oh, if I just subtract B and add B, right, then I'm looking at A minus B plus B minus C. And in that way, I was able to just add those two differences that we already had. And I'm bringing this up not because it's the same relation, but we're still looking at differences. And this same technique, where we say, oh, A minus C, I'm going to write that as A minus B plus B minus C. That same technique will work when you look at the transitivity here, right? You're going to suppose that x is related to y and y is related to z. Right, so that gets you, each of these things gets you a statement, right, that we get to use for free. And then to answer the question, is x related to z, you're going to look at x minus z, right? You want to show that that's an integer. And you're going to use that same algebraic technique to rewrite the difference, x minus z, as the sum of the two differences.
Was that 4.34?
Hold on. Yes.
All right, so should I just, I remember I think I had to do this for assignment 5 as well, where I just had to pick a number or 3 numbers.
Well, that was showing that something wasn't transitive. If something's not true, then
You
an
find a
example,
counterexample.
which we call a counterexample, suffices. To show that something is true, we have to show it's true always. So an example might help you get a feel for the problem, but it's not a proof that something is generally true.
Okay, so with this technique, with the x minus y plus y minus z.
Mm-hmm. So, okay.
Basically what we're doing is we're just following a logical progression that shows that both of those maintain their identity as integers throughout the entire process.
Right,
so the end result of both those have to be integers.
Yeah, like we start this part by saying suppose x is related to y and that y is related to z. That should tell us something about x minus y and y minus z, right? Which then we can pull into our conclusions.
Gotcha. So really you would just you conclude by just saying that because they stayed integers all the way through, it has to be transitive.
Right, like
because they are integers.
Because we have an integer plus an integer, right?
Mm-hmm.
So that if you add two integers together, you're not going to end up with a decimal part.
Okay. And then 4 is the only one I haven't started yet.
Mm-hmm.
Functions was also in chapter 4, right?
Yeah. Okay. So in part A, that's a counterexample one, right? You're going to show that it's not injective. That was in chapter 4. I think that was in the beginning of chapter 4, maybe. It might have been the first section. Here's something to know about about injective. If a function, which I'm just going to call f, it's not the same f that we're in fact, maybe I'll just call it. I'll say if a function h, I'll call it h of x. Being injective is equivalent to saying that if whenever like h of a equals h of b implies a equals b, it means that you can't double up on outputs. It means that if you happen to find values a and b to plug into the function that give the same outputs, which is what it means to say that h of a is equal to h of b, that the only way that would happen is if they were the same input to begin with. So
gotcha.
In part A, because you want to find a counterexample to show that f is not injective, so that means you're going to find actual numbers
that have two numbers that map to the same output.
Yes. So you want f of a to be equal to f of b. So you're going to find actual numbers for a and b, but a is not equal to b. You want two different numbers that give you the same output. That's all you got to do in part A. And then in part B, you're going to prove that G is injective. So an example won't suffice. In part B, you want to start out by saying, let's suppose G of A is equal to G of B, and then you want to show that A is equal to B. And I'm going to bring you to an example where we did one like that in class. Oh, here we have some one-to-one functions and not one-to-one functions. Okay. Here in example 4.9, we proved that the function 3x plus 5 is injective. So we said, let's suppose f of a is equal to f of b. That got us some conclusion, and then we were able to do some algebra and deduce that a has to be equal to b. And that's enough to show that it's injective. This example, really you can use this example as a model and a guide for how to approach part B of number 4.
Okay. There it is. Just pulled that up. Okay. Well, I will go over this and I will write up 8 and I will finish neatening up number 5 because number 5 took forever.
Oh, how long did it work out in the end? Did you check and it like, because when you're doing the extended Euclidean algorithm, you can always check your answer, right? Like.
Yeah. So this is the dirty version.
Uh-huh.
So I got about you can't see it on camera, but about
I
got about 2 pages worth of stuff
I can
here.
see it. Yep. Yeah. I see it. That's good. But it worked out in the end, like it checked out.
I was still doing. Yeah, I don't know if you can see it. I was still doing the check complete. Every couple of steps.
Good. Yeah, good.
So I was checking along the way. But yeah, that was more tedious than anything else.
Mm-hmm. Yeah, it is tedious. I think that's a good word for it. But it'll pay off in chapter 6, and we're going to find that that's a good way to find inverses of numbers.
Nice.
That when we're working like mod something really large.
Like what? Mod 100? Mod 2000?
Mod like 12,713 or something.
Good Lord.
But it's like, because Euclidean algorithm, it's the algorithm itself isn't, the length of the algorithm doesn't really depend on how big the numbers are. Like, you could have huge numbers and the algorithm terminates in just a very few steps.
A couple steps, yeah.
And so it's something that is sort of doable by hand, and then it actually has application and encryption. So where it's actually used, you end up, people write a script and just have computers do it, which obviously, like, they could do however many calculations per second. So it's actually really efficient.
Yeah, the mod program was really useful for that cryptography thing. Cute message, by the way.
Oh, yeah, good.
My mom got a kick out of that.
Good.
All right. Well, I think that's pretty much all I needed.
Okay. All right. Well, reach out if you have other questions.
Absolutely, I will.
Okay. Enjoy the rest of your day.
You as well.
Thanks.